Hi all. In this video we discuss a few facts about angles and chords that you will find useful as you're doing your homework in Sketch 18 of Math Through the Ages, which is about trigonometry. We begin by talking about angles inscribed in circles. So as you would expect, we begin with a circle, and on that circle we select 3 points, one of which we designate as the vertex of the angle. In this particular instance, we have points A, B, and C on the circle, and A will be our vertex. You might notice that we have labeled the measure of angle BAC as alpha. And now what I want you to do is imagine if we were to take the vertex A and move it to the center E of the circle while leaving the other points B and C fixed, what that might have in terms of effect on the measure of the angle. So we're moving the vertex A to the center E, and we are wondering what happens to the measure of the resulting angle. It certainly looks like the angle will become bigger, and in fact, what happens in every instance is that we double the measure of the angle. And that's the main theorem, that if angle BAC has measure alpha, then the new angle BEC with vertex at the center has measure 2 alpha. I don't plan to derive this result here. However, if you simply draw in the segment from A to E, you will see that produces 2 isosceles triangles, and using facts about isosceles triangles, you should be able to verify this result without too much trouble. Now we want to look at a special case of the previous result. Again, we have an inscribed angle, BAC, but this time the points B and C are special in that if we draw the segment joining B to C, it passes through the center of the circle E. So that segment is a diameter of the circle. Now, if you look at the angle BEC, that's a straight angle. It's a 180-degree angle. And from the result that we had on the previous slide, we know that the measure of that angle should be double that of the inscribed angle BAC. That then forces angle BAC to have measure 90 degrees. So it will be a right angle. Now an inscribed angle of this type, we say that it is inscribed in a semicircle because the diameter BC naturally divides the circle into 2 parts. And here then is the result. Any angle inscribed in a semicircle is a right angle. Now let's talk a little bit about chords in circles. The very earliest investigations of trigonometry didn't involve the sine and cosine functions as we know them today. Instead, they involved measuring chords in circles of some given radius. So now I'd like you to focus your attention on the top figure, where we have a circle centered at E, and we have a central angle alpha, the rays of which determine 2 points, A and B, on the circle, and we can join A and B with a segment. That segment, or rather the measure, the length of that segment, is called the chord of alpha. One thing that we would like to be able to do is pin down how the measure of that chord, that is the chord of alpha, is related to our modern day trig functions. And here's the relationship. If we let alpha be a central angle in a circle of radius r, then 2r times the sine of alpha over 2 is equal to the chord of alpha. I think it's worthwhile for us to see why that is true. So let's refer to the figure at the bottom of the screen. where we see that we have bisected angle AEB, and the bisector cuts the isosceles triangle AEB into two congruent right triangles, where, of course, the angle AEC is of measure alpha over 2. So if I want the sine of alpha over 2, I just use right triangle trigonometry, and that's opposite over hypotenuse, where the opposite side is of length AC and the hypotenuse of length is of length R. Now AC, however, is half of AB, so if I take AC and replace it by half of AB, I get that the sine of alpha over 2 is AB over 2R. But remember that AB is the chord of alpha. So that replacement gives us that sine of alpha over 2 is equal to the chord of alpha divided by 2R. And then if we multiply by 2R on both sides of the equation, we get the result of the theorem.